welcome to Topcast and episode 89 of the series. This one is chapter 4 of The Science of Can and Can't by Chiara Marletto. And the title of the chapter today and the title of this episode is Quantum Information. Now, I know that many people who watch and listen are not necessarily people with a physics background. Some are, but I think they are in the minority. Indeed, physics itself is becoming increasingly a minority among school students. I'm not exactly sure what the distant historical trends were, but I know that today in Australia and globally, broadly speaking, in the Western tradition, fewer and fewer students are electing to take physics in the senior years as compared to taking things like biology or chemistry or even sports science. Much less to say people taking on physics at university as a proportion of all people who attend university. Now, I'm not saying if this trend is neither good nor bad, neither here nor there. The fact is that fewer and fewer people, as a proportion of the entire population, are comfortable with physics and with physics terminology. That's one thing. But even if people do choose to go off and do some physics at university after having done it at school, the overwhelming majority of people who take physics at university at the lower undergraduate level, let's say, are engineers and chemists and maybe people who go into medical fields like radiology and so on. They are not predominantly physicists in the main. And even those people who take physics, the engineers and the radiographers and so on, those people can tend to find areas of physics quite esoteric themselves. So, for example, quantum theory is a typical case in point. Some people who do some early physics at undergraduate level at university might never even come across quantum theory to any great deep extent anyway. They're regarded as an esoteric curiosity that only comes up at dinner parties or at discussions at the pub or something like that. But even if you're someone like me who was determined to do something like astrophysics and who had to take a lot of units of quantum physics along the way, there are still parts of the physics canon, so to speak, that are esoteric. And one of them is what we're about to talk about today, which is quantum information theory. Now, I can't remember exactly when I first heard about quantum information theory. I think it was when I was beginning to do quantum physics and I thought, this is strange and weird and technical enough. And then you hear about this thing called quantum information theory and you think, how much more wild can this get? And I remember picking up a few texts that were around. This was decades ago, just the beginnings of quantum information theory. And I struggled to understand what was being said and I never really pursued it. And ever since, when I've tried to investigate it further, I've always found it dry, which is a hint that I'm finding it difficult because I'm finding it uninteresting. And that's typically because of the way it is explained. Quantum theory itself is rarely well explained, except in the work of people like David Deutsch and David Wallace and so on, who actually get to the heart of the matter about what's going on during the experiments. Well, quantum information theory doesn't even bother with many of the experiments. It's often just presented as a dry mathematical tool that's used by people who work in the really rarefied areas of the theoretical part of physics. So it was never really relevant to me training to do astronomy. So the reason why I'm saying all of this is because I want to give a plug to the book. I really think you should get hold of the book because this chapter in particular does an excellent job on two fronts, related two fronts. First is that it manages to make quantum information interesting. It made me want to keep reading to see what Chiara was going to say next because she's presenting it in a way that I found new and refreshing. And because of this problem being solved of how do you make this weird subject interesting, it became easy as well. And that's always a lesson for all of us. If something is interesting, then it can tend to become more easy. And I've said this before, if you ever had trouble with something at school, it's not because you were ever incapable of doing that thing. It's because you never found it interesting. And you probably never found it interesting because the person presenting it wasn't making it interesting. Subjects just are inherently interesting. Physics, for example, is inherently interesting. If you are not captured by a lecture about how stellar evolution works and what stars can ultimately end up as, then that lecturer is really working hard to make things boring, because it is just naturally fascinating. And I think everything ultimately must be like that in some way. When you get into really deep explanations of things, they're just really fascinating, inherently fascinating. And Chiara's managed to find some of the inherently fascinating parts of quantum information. And I say you really have to get the book, because my podcast here is no substitute for reading the book at all. And to make that point, I'm skipping the first few pages of this particular chapter. And remember, I'm also skipping whole sections of the book, whole chapters, so to speak. There are these little interstitial bits in between the chapter proper parts. There are little fictional stories which are absolutely worth getting. They're parables of a kind. They have a lesson, and the book is worth getting, if only for those. So after skipping these first few pages, I'm going to pick it up where Chiara begins to describe this ball and cups game, which many people will be familiar with. The most basic form, which is the one that she is describing, is where there are two cups and there is one ball. And the person who is in charge of the game hides a ball under one of the cups, and then the person playing the game has to guess which of the cups the ball is under. And this leads to this curious distinction between people who subjectively experience unpredictability and people who subjectively experience certainty. So in that particular game, of course, the person playing the game who does not know which cup the ball is under has a 50-50 chance of guessing which cup the ball is under. But the person who is in charge of the game, of setting up where the ball is going to go, knows with certainty, probability equal to 1 if you like, that the ball is under that particular cup and not the other. So there is an asymmetry there. And this is a kind of parable of a sort that is going to lead into the idea of objective uncertainty and subjective uncertainty. So let me pick it up where Chiara begins to refine our understanding of some otherwise mundane terms. So as I say, Chiara's just been explaining how this ball and cups game works. And I'm picking it up where she writes, quote, "The risk in games of chance is due to a counterfactual property. It is the impossibility of correctly predicting something with certainty. I shall call this property unpredictability. In the shell game of my childhood," just by the way, Chiara refers to this ball and cups game as the shell game. "In the shell game of my childhood, what is unpredictable is the position of the marble or the ball relative to the cup. Interestingly, in this case, the unpredictability is not objective. It exists only for the player. From my point of view, the probability of correctly predicting the marble's location was 1 in 2. But someone who had the full details perfectly knew its position. The unpredictability in this case is therefore apparent to the player only because he or she does not have complete information. The person who sets up the game, by contrast, sees an entirely certain, predictable, and deterministic situation. It seems that, just like in this game with marbles and cups, most unpredictability in everyday life is due to lack of information. When the weather forecast is uncertain, and the weather unpredictable as a result, it is because the information about the initial condition of all the particles in a given region of the atmosphere is imperfectly known. Coin tosses are unpredictable because the initial conditions of the coin and environment are largely unknown. The degree of unpredictability is then quantified with probabilities. The probability of some unpredictable event happening expresses the extent to which one expects it, given what one knows. When asked, "What will the weather be like tomorrow?" you can reply, for instance, "I don't know for sure, it's unpredictable, but there is a 90% probability that it is going to be sunny," and so on. All unpredictable behaviours were once supposed to be the same as in this game. Not objective, but tied to a specific viewpoint. If given complete information about the actual state of affairs, there is no unpredictability. The latter appears only if one has incomplete information. Though this belief might seem intuitively true, it was wiped out by the discovery of quantum theory in the first half of the 20th century. In quantum theory, unpredictability does not arise just from a lack of information. It is inherent to the physical world. even when everyone has all the relevant information. It is objective, end quote. All right, so just my comments here. The thing here, and if you're a viewer or a listener to my series on the multiverse, Chapter 10 of The Beginning of Infinity, you will know that subjective randomness is in fact all we have, because objectively there is no randomness. So we have this subjective feeling that what is going to happen in the future is uncertain, but God's eye view of the multiverse, what's happening is unfolding according to the laws of physics, which are not probabilistic, they're deterministic. They are determining precisely what is happening at every point, at every moment in the universe. And just an aside, of course, that is not always the best explanation of anything that happens to be happening at any given time. Knowledge creation is the most important exception to this rule. When you want to explain what's going on, simply saying that things are determined according to the laws of physics is not the best relevant explanation. Throwing that aside, the point here is that subjectively we lack knowledge of everything that's going on. That just necessarily is the case. Things are uncertain from our perspective. And when I say our, I mean individually and collectively as an entire civilization. And worse than this, as Chiara's just hinted at there, and as many listeners will already be aware, the laws of physics mandate we cannot know simultaneously to infinite precision all of the factors that will come to bear on whatever outcome we're about to see in the future. We'll come back to this when we speak about observing, copying, and measuring, which is part of this chapter, and is a new window into viewing these particular things. And we'll see how those things, observing, copying, and measuring, are actually related. Okay, back to the book. And Chiara writes, "It is rather unfortunate that quantum theory has acquired, in the collective imagination, the status of a quirky beast that is incomprehensible, but worthy of attention, because of its weird and bizarre demeanour. You may recall the words spooky action at a distance, used by Einstein to describe quantum entanglement, or the creepy idea of locking a cat inside a box with poison, the notorious thought experiment that Schrödinger envisaged to illustrate quantum superpositions. With catchy phrases, the press has promoted the view that quantum theory is destined to remain a complete mystery. Leaving the good old days of Newtonian physics behind, when the world used to make sense, we now have to resign ourselves to a new and alien picture of physical reality which accords with the experimental evidence, but whose explanation of the universe is baffling." Pausing there, my reflection. I think Chiara's being polite to her colleagues, not to her close personal colleagues, but to the wider physics community. I don't think we can blame only the press here. I think we can absolutely blame a generation or two of physicists and science communicators for deliberately at times mystifying and obscuring what quantum theory is all about. And I think they have done it, consciously or not, for the same reason that priests, to some extent, used to do this with holy books. It ensures that they maintain their authority as the experts you need to go to, whose opinion you're going to seek, whose feet you're going to sit cross-legged at, and listen to the deep wisdom because they are the ones in possession of it. Very few physicists are like, for example, David and Chiara and associates, who speak very clearly about these issues. Some like to revel in the mystery, and so long as they revel in the mystery, people will keep looking at them as kind of like gurus. And this is not a good thing. We need to demystify all areas of science that we possibly can, in particular quantum theory, because it's been mired in this bad philosophy, this bad way of trying to explain what is really going on, and this fear to some extent of trying to grapple with what it's actually saying about reality, namely the multiverse. Now, the interesting thing here is that Chiara's not actually going to even mention the multiverse in this chapter. In fact, she doesn't even mention it in the entire book, except in the acknowledgements. Now, there is an important reason for this that I'll probably come back to later. And I think the reason is, I haven't talked to Chiara about this. I cannot possibly speak for Chiara on this point. But my guess is that she's using an important heuristic now. It's a heuristic that I heard from David Deutsch many years ago, I think just after the publication of The Fabric of Reality. I think someone was interviewing him about The Fabric of Reality. And he said at the time words to the effect that he thought it far more important to just explain the best explanations that we had and to make progress by taking those explanations seriously, taking them for granted in a certain sense, and just building on top of them, standing on the shoulders of the giants that were those explanations, and going further and seeing further, rather than simply fighting the old fights, debating the old debates, trying to knock down all of the bad alternatives. If you want to make progress in genetics and biology, there's no point standing up on stage, spending most of your career and your working life debating with creationists. That's not a good way to make progress in science. So similarly, if we're quantum physicists, like Chiara, we just take it for granted that what quantum physics is saying about the world is the multiverse is true, okay? We really do live in this multiverse. So we don't have to worry about trying to re-explain what the multiverse is, to defend the multiverse at every single point, if we're going further and building on what quantum theory is. It's for the same reason that anyone who writes a book about genetics or evolutionary biology does not have to spend multiple chapters saying why evolution by natural selection is actually true and why creationism is actually wrong. You just take it for granted. And so my guess is that Chiara is just taking for granted the reality of the multiverse, which I think is great. But just to say that this stuff about the weird, catchy phrases have not only been instilled into the scientific conversational zeitgeist, so to speak, by the press, by people reporting on science, and even today some of the physicists themselves, the way in which they talk and publicly promote, especially quantum theory, has overtones of weird, mystical, almost spiritual kind of overtones, and it has a lot of baggage associated with it. And we can do away with all that simply by taking it realistically and accepting the fact there's a multiverse. Anyway, we digress. Chiara goes on to say, quote, "None of this nonsense, none of this is even remotely fair to quantum theory. Yes, the quantum world seems bizarre and counterintuitive at first, but in reality it is fascinating, subtle, surprising, and above all, not mysterious. It can be understood. The more it is understood, the more exciting it becomes. It is true, though, that quantum phenomena cannot be expressed entirely in terms of familiar analogies. As you are about to discover, there is a genuinely new, dazzling set of properties that quantum systems have, which are conceptually far from our everyday worldview. And they are all based on a set of simple counterfactuals, which I shall now explore. Incidentally, quantum phenomena are important for the progress of our civilization because they allow for the enhanced information processing capabilities of quantum systems, which outclass non-quantum information media, such as those deployed by the classical computers we use nowadays. The quantum counterfactuals are the fuel for the next technological revolution, the universal quantum computer. A universal quantum computer is a universal computer, that is, a computer that is capable of performing every computation that is allowed by given laws of physics, as I explained in Chapter 3, that relies entirely on quantum theory for its information processing. The computers we currently use are classical because they rely not on quantum phenomena to perform computations, but on entirely classical mechanisms. The theoretical description of the universal quantum computer has been around since the 1980s, and its features are very promising on paper. It has superior computational abilities compared with classical computers because its elementary information units, the quantum bits, can explore a much richer set of possibilities than simple classical bits. The effect of this richness, which is entirely due to quantum physics effects, is that the universal quantum computer can be faster and more efficient than a classical computer when it comes to certain computational tasks. Searching a large database, factoring a number, etc. What is important here for you to have in mind is that the leap in possibilities that a universal quantum computer would bring about is analogous to that brought about by the introduction of the classical computers in the first place. It will make an entirely new class of technological improvements possible in the realm of information processing. Alas, the actual realization of a universal quantum computer has proved to be very challenging in practice. This enterprise has engaged some of the finest minds among physicists, engineers, and material scientists. Numerous IT companies such as Google, IBM, and Microsoft, and startups as well, are now trying to race towards the first viable prototype of this machine. but we are still quite a way away, even if we are definitely getting closer. Pause there, my reflection. Okay, so this thing about being quite a ways away, it's been said for decades now. And we hope that we're getting closer, and it seems as though sometimes we're getting closer, and then it seems like we're not. We often get these announcements, especially by the very companies mentioned there by Chiara. Google has announced more than once over the decades now that they've got a functioning quantum computer of a kind. I don't buy it. And the reason I don't buy it, well, yeah, maybe they have some weird technology they're hiding from everyone. I think we'd know. I think there'd be an actual leak from the company. I mean, there would be high financial incentives for anyone within that company working on such a technology to actually take the information somewhere else and sell it at a really high price. But that's not happening, okay? Once we have a quantum computer in one place, what I'm saying is we'll end up having a quantum computer in lots of places simultaneously. Or the word will quickly get out. That's the first thing. The second thing is, as I've mentioned in previous episodes, I think the multiverse chapter in particular of The Beginning of Infinity, the engineering difficulties with quantum computation something I'm a little familiar with. I'm only a layperson in this. I'm a layperson who takes a special interest, but I'm definitely not an expert. But because of my special interest, I've visited one of my local universities who actually have a centre for quantum computation, the University of New South Wales. And I've had some discussions with some of the people there, including the person that runs the entire place. And their quantum computer, the best they can do at the moment is 1 or 2 qubits. You hear, when places like Google make these announcements, they go, oh, we've got heaps and heaps of qubits, hundreds of qubits or something or other. And now and again you see press releases about this. I think it's all a scam. I think it's all a scam because of the way in which I understand at least some of the hardware works. I've heard tell that there are alternatives to the way in which you could have this quantum computation happening. I don't fully get these alternatives, but the way in which I've heard these quantum computers work, at least at the University of New South Wales, I think they use ion trapping. They use phosphorus type atoms, and they have to keep these things very, very cold. They have to keep it cold so that the information doesn't leak out, so to speak, so that and we're going to come to this in the chapter actually that we're reading right now, so that the atoms remain entangled so they can do the job of computation. Entanglement's this technical term where the two atoms are kind of behaving like the one system rather than as two independent things. So that's one thing. And the only way to ensure this entanglement remains in place, at least in this particular setup, is to have them not moving around very much. Once they start to move around, they decohere. Decohere, fancy name for lose the information. They become entangled with the rest of the environment. But you don't want them entangled with the rest of the environment. You want these two atoms, these two particles, to only be entangled with each other in order to do the job of computation. We can rather think of it like, this is a poor analogy, but you can rather think of it like the electricity inside of the computer is something that you want to keep inside of the computer. Once the electricity starts to get into the computer from the outside, you've got serious problems. Or once the electricity that's in your computer starts leaking to the outside world, you've got a problem. Okay, it's a very delicate mechanism. You don't want additional electricity, additional electrons wandering through the circuits of your computer. Okay. So in order to maintain the entanglement of the particles in the quantum computer, at least at the University of New South Wales, and I think this is the way many different kinds of races towards an actual quantum computer are working, is you have to get these things very cold, and you need to get down to near absolute zero. And I've told this story before, and at UNSW, what they do is they use liquid helium, which gets you down to about minus 270, something like that, but that's still not cold enough. And so what they do is they use evaporative cooling, and so they have this isotope of helium, helium-3, the light isotope of helium, and they use that to evaporate away from the helium-4, in which the atoms of phosphorus are being bathed, and as that evaporative cooling happens, you can actually get down to minus 272 point something or other. So it's very, very close to absolute zero, and they need to get down to that so that the things remain entangled with one another. Now, an interesting question was, I said to them, where do you get helium-3 from? How do you go about refining that? And the curious thing was, I don't know if they were supposed to tell me this or not, but they did tell me, maybe it's public knowledge. They said that, well, the American Army, of all people, sponsors their project, sponsors their race towards building this first quantum computer. Of all the people, the American Army. And I said, American Army, like, why the American Army? Well, it's a bit of a deal, right? The project that UNSW, the University of New South Wales, is running requires the helium-3. And guess what? The American Army, being the military, would like to ensure that they have access to the first quantum computer that's built. So I'm sure they're sponsoring a lot of such projects, okay? America, for defense reasons, wants to ensure they're not left behind. And so they are supporting lots and lots of people financially in order to build a quantum computer. So there's definitely big money in it. But the way in which the American Army gets their helium-3 is from the radioactive decomposition of uranium, I think it is, might be plutonium, whatever, one of the radioactive materials inside of their nuclear bombs. So their nuclear bombs are irradiating this stuff, and they collect it in big balloons, and then they send it to people like the University of New South Wales to do research with in quantum computation. So that's a curious way in which nuclear bombs are assisting with research towards quantum computers. Anyways, for even more details about that, again, my multiverse series has some more details. And I'm picking it up where Chiara says of herself, and I would also agree with this, quote, "I belong to the cohort of people who look at technological developments in awe, with optimism and high expectations, but are ultimately more interested in the foundations of the theories that allow such technology to exist. What is it precisely about quantum media that makes them capable of supporting such super efficient quantum information processing? What can one learn by looking at the foundations if the technology is already pushing ahead? In fact, by digging into the foundations of quantum theory, we stumble upon a surprising fact. All properties of quantum systems, which are crucial for the universal quantum computer and the related quantum technologies, rest on a few elementary counterfactual properties. In Chapter 3, I explained that information media are systems with attributes that can be flipped and copied. Quantum systems have these counterfactual properties and therefore are information media in their sense. But they have more counterfactual properties, making them so much more powerful. To see what these properties are and understand why quantum systems are a more powerful kind of information medium, I shall invite you to look again at the game of chance with cups, now through the lens of information theory. The two cups together with the marble are, using the terminology of Chapter 3, an information medium. They can contain a bit of information encoded in the position of the marble, as you can see in the figure on the screen from page 111 of the book. When the marble is under the cup on the right, it encodes the value 0. When it is under the cup on the left, it encodes the value 1. You can imagine a standard procedure to set up the game. First, toss a coin. If the coin shows heads, put the marble under the cup on the left. If it shows tails, put it under the one on the right. At this point, for the player, the bit is perfectly randomized and maximally unpredictable because it could hold the value 0 or 1. The marble could be either under the cup on the right or that on the left, each with probability a half. For the person who sets up the game, however, the bit has a definite value, either a 0 or a 1. They know where the marble is. Now imagine setting up the game with systems that behave according to quantum theory. Not simple information media, but quantum information media. What would change in the game? Our quantum game involves a photon, a quantum particle of light, instead of the marble, and two possible paths instead of the cups. Pausing there, my reflection. As you might guess, again, if you've read The Beginning of Infinity, if you've listened to my podcasts on The Beginning of Infinity, what we are about to describe is the Mach Zender interferometer. What I like to remind people of, as we're discussing something like this, is that these are physical objects. These are really existing physical objects. They're not abstract ideals, and because they're really existing physical objects, you just have to accept the fact they're obeying the laws of quantum theory. They might violate your common sense, but so much for your common sense. You might think you know how a mirror works, or a crystal works, or how light bouncing off of a surface works, so to speak. And you could be completely wrong about all of it. So we have to take at face value to a certain extent what is being said here. But to another extent, you can always go and check yourself. You can always do the experiments yourself if you were willing to try hard enough. You can certainly read about the results. You can watch people doing these experiments. You can see for yourself. You can check for yourself. But there is no lie being told here. There's no fiction being told here. It simply is the case that there are some strange and unusual results that we're about to discuss. Let's go back to the book. So we're discussing this quantum game involving a photon. And Chiara writes, a source emits the photon. Then the photon can travel straight along the horizontal path or along a vertical path. The photon and its path constitute an information medium. They can encode a bit. If the photon travels on the horizontal path, it encodes a 0. If it goes on the vertical path, it encodes a 1. It is possible to set up the game by following the randomization procedure I explained earlier, but this would not lead us to a quantum game. For example, someone sets the photon to travel vertically or horizontally according to the output of a coin toss. Again, the chances are half for the player to guess correctly which path the photon is on. As you can see, this version of the game is not different from the marble because it does not use quantum properties of the photon in any way. We need to explore some other kind of setup using the quantum properties of the photon. What is the quantum stuff that a photon can do while a marble cannot? It can be prepared in states that are exclusively quantum, in the sense that they do not exist according to classical physics, but only under quantum physics. An example of these chiefly quantum states, which is relevant for the photon in this example, is what I shall call a superposition of the horizontal and vertical path. In order to understand what kind of state this is, how it is related to the states where the photon is on a definite path, and what counterfactuals have to do with all this, we need to look at a definite experiment where the photon is prepared in a superposition of different states, and then certain measurements are performed on the photon. This will tell us how the superposition is in a certain sense similar to the state of the marble, but is fundamentally very different. The photon, after having been emitted by a source, can be put into a superposition of paths by guiding it through a special kind of crystal, which, when interacting with the photon, causes it to split along two paths, horizontal and vertical, as in the figure. If you were to guide a beam of light made of lots of photons through this crystal, you would see that the beam is split across the two paths, horizontal and vertical, which is why sometimes this crystal is called a beam splitter. But here I am talking about a single photon, not a beam of light, and what it means for it to be split can be understood only with quantum theory. So what do we mean by the photon being split across two different paths in a quantum superposition? Well, one key aspect of the superposition is that after passing through the crystal, the photon could be found with probability a half on the horizontal path and with probability a half on the vertical path. When the photon is in a superposition of different paths, it is impossible to predict with certainty which path it is on. Its path location is unpredictable. Experiments happening daily around the globe in the quantum laboratories confirm this behavior to the highest precision. Pausing there, my reflection. Okay, so on this point about split. Now, Chiara here is avoiding the terminology of broader quantum theory. The way I would phrase this, if I was explaining this to someone, is that, of course, the photon is a quantum object. And as a quantum object, it is made up of fungible instances. And so what a photon is a multiversal object, such that when it collides with a physical crystal of the kind that Chiara is describing, or it could be a half-silvered mirror, whatever you want, half of the instances bounce off and go vertically, and half of the instances are transmitted through the crystal and go horizontally. So this is what the splitting is. The splitting is the differentiation of the instances. Why does it happen? Because it's possible that it could happen. The laws of physics say that this is what happens. It's almost kind of like when people ask, or if they do ask, why does an object in motion stay in motion unless acted on by a force? Well, it just does. If there's no force acting, then there's no reason for it to change its course of motion. This is one of Wittgenstein's lines, my spade is turned. You can't explain it further. This is just what the laws of physics say. And so if you do have this possibility, this physical possibility of the photon taking one path or the other, then it can indeed take both paths. And it does indeed take both paths in this particular situation. And it's testable. You can test the claim that it only takes one path by doing the experiment. And if you have the hypothesis it must only take one path, well, you will find, repeating the experiment, that in fact it takes both paths, repeating the experiment often enough. So it approximates what happens in the multiverse. Okay, but back to the book. Chiara writes, does this mean then that when the photon is in a path superposition, its properties are exhausted by saying with what probability the photon is on one path and with what probability it is on the other, just like for the marble in our classical example with 2 cups? No, in reality, the story is much more subtle. Quantum superpositions are not about probabilities. The photon is not a randomized bit, even if, in some instances, it can look like one. The first difference from a randomized bit, such as the marble, is that no one can predict with certainty which path the photon is on. Even the person who prepared the photon superposition cannot predict that. The unpredictability of the photon path is absolute, unlike in the case of randomization. Pausing there, just my reflection. Now, the reason for this, by the way, is because, well, as we're going to get to, everything about what the experimenter is doing and what a person who tries to make a measurement here is subjective. And the reason that it's subjective is because you're in a particular universe with a particular set of instances of the photon. Copies of you are in the other universes with instances traveling along the other path. And so when you make the measurement, you will always only ever detect the photon traveling along one of the 2 paths. You can't possibly detect it traveling upon both paths, even though it does. Even though it does travel along both paths. It's in this superposition of traveling along these paths. But you will only detect it along one of the paths because of the differentiation of the universes. And Chiara's just saying, here, this is the way it is. This is the way it is. Accept it. She goes on to say, quote, the person who prepared the photon knows all the details about the situation, yet cannot predict where the photon is. The photon is in a quantum superposition of 2 different paths. When in that state, it does not have a definite position. And if you were to measure its position, that measurement would have an unpredictable outcome. So, the quantum unpredictability associated with superpositions does not come from the lack of information about the preparation of the photon. Just pausing there. Yeah, just to emphasize that point, the real-life version of this experiment requires preparation of the photon. Preparation of the photon requires something like the energy of the photon to be tuned. You need to know what the frequency is. And then you fire it in a particular direction. And given a particular setup of the apparatus, these things again are physical, then upon encountering the crystal, which has a certain thickness, which has certain properties, then it will cause phase changes in the photon, okay, the way in which the photon reacts to striking the crystal, to passing through or bouncing off the crystal. And even that passing through and bouncing off is not a simple process at all. That is a physical interaction. When a photon passes through something like a crystal, what's actually going on is the photon is absorbed by the atoms of the crystal and then re-emitted. Absorbed and re-emitted, absorbed and re-emitted. This process goes on. It actually slows down the travel time of any beam of light or ray of light traveling through it, because the absorption and re-emission of these photons takes time. Even though the photons always only ever travel at the speed of light, the absorption re-emission thing takes time. So it slows the photon down as it goes through the crystal. And this is, by the way, why you need this second crystal, as we're about to get to in the full Mach Zender interferometer, so that the 2 photons that travel along these 2 different paths actually travel along exactly the same length paths. Almost exactly the same length. They're out of phase by a certain amount, and because they're out of phase, you get a certain amount of interference, which always causes the photon to travel in one direction and not the other. Again, see my multiverse series for the entire explanation of this. Okay, so I'm skipping a little bit and I'm picking it up where Chiara writes, quote, the second significant difference can be seen by repeating the game after having played it once. For the marble, you randomly put the marble under one of the 2 cups by tossing a coin, as I said earlier. Then you repeat the coin toss and, according to the coin value, reposition the marble under one of the cups. The player has still the same chance of guessing correctly where the marble is, 1/2. Indeed, adding uncertainty to an already uncertain situation can only make things equally or more uncertain. Randomizing once or twice or 100 times leaves the unpredictability the same. Repeating the steps of the preparation does not change the odds of guessing correctly. Now look at what happens with the photon. To repeat the preparation of the quantum superposition twice, you need to let the photon through the crystal twice. In a real experiment, this can be done by arranging a second crystal after the first and by setting up a system of mirrors so that the photon would go through the first crystal, bounce off the mirror, and go through the second crystal when travelling on both the vertical and horizontal path. Which path will the photon be on after encountering the second crystal? If you think of each crystal as randomizing the photon path, judging from the marble example, you would expect the photon to be found with probability a half on one path and one half on the other. But this is not how it goes. The photon, after encountering the second crystal, will invariably end up on the same path as it was before, the horizontal one. If you believe that the crystal is simply randomizing the photon path, the fact we have uncovered seems to imply something impossible. That applying the same randomizing procedure, the crystal twice, produces something certain, not random. This conclusion cannot be true. If it were, you could go to a casino and always win simply by waiting for the dice to be rolled twice, or the cards to be shuffled twice. We've reached a contradiction. As always happens with contradictions, something in the assumptions has to give. The revelation here is that the crystal is not a randomizing operation, even though it looks like one at first. The quantum superposition, created by the beam splitter, unlike coin tosses, dice throws, and the like, cannot be described with probabilities only. It is something else. I first properly learnt about this surprising fact during my doctoral studies from Arthur Eckert, who in the early days of his pioneering work on quantum cryptography had to think hard about how to explain to an incredulous scientific community what was so special about quantum systems as opposed to simply randomized phenomena. The explanation for this counterintuitive phenomenon resides at the heart of quantum theory. So much so that this fact alone can be taken as a signature of the photon being a genuine quantum mechanical particle. Just pausing there, my reflection, just to emphasize this. We can see on the screen the picture here of what is in Chiara's book, actually, of the Mark Zender interferometer. And the way in which she explains what's going on is that it seems as though what the crystal is doing is perfectly randomizing things. After all, if you perform the experiment one photon at a time, then you can't predict whether it's going to go straight horizontally or up vertically. You just don't know. You can put detectors after the crystal in both of those places. And sometimes it will go straight through and sometimes it will go up. Sometimes it's horizontal, sometimes it's vertical. You don't know. It just appears to be completely and utterly random. And so putting a second crystal there should be seemingly completely and utterly random. Now, for an explanation of this, and I don't want to go into it now because it took me some 15 minutes to explain it in the Multiverse series, but you can find it if you go to Talkcast episode 23, on YouTube in particular. I've been calling it Chapter 10. It's Chapter 11. Chapter 11, the Multiverse. Chapter 11, the Multiverse, Part 0. And in that Part 0 there, if you skip to like the 42-minute mark, and the 42-minute mark, I spend a long time going into excruciating detail about the Mark Zender interferometer and the mechanics of what's going on from one perspective that might give you an insight into what exactly is going on here. Now, we're about to have another perspective as well. And that other perspective is, as Chiara says, the assumption that it's simply randomizing things, that it simply is purely random whether it goes horizontal or goes vertical, is not quite right. As Chiara said, and I'll say it again, and she says she credits Arthur Eckert for this, quote, "What makes the photon so different from the randomized marble in the original game is that once it has gone through the first crystal, once it has, another one of its physical properties, not the position or the path, is perfectly definite. The property is that of being in that particular superposition of paths. What's more, there is another counterintuitive fact. Letting the photon through the second beam splitter and then measuring where it is one way of measuring that other property. That is, measuring which superposition the photon is in." Okay, just say that again because that's such a subtle point. So once the photon goes through the first beam splitter. In other words, the first half-silvered mirror, the first crystal. Everything is not equal. It depends upon how you've set up the experiment. The crystal can have different thicknesses. The photon can have different energies. There are physical properties here that you can play with, such that once that photon has gone through that first part of the apparatus, once the photon has passed through the crystal, there is something about it that is perfectly definite. What is that something? Well, as Chiara's calling it there, it is this superposition property. It's in a particular superposition of paths. And the reason we say this is because, well, in my understanding anyway, it has a certain kind of phase. And the way I describe it in that other episode is that, well, in the wave theory of light, it's sort of vibrating upwards. It's like a crest as compared to a trough. It could be one or the other. Now, there is a quantum analog of this, okay, the more precise way of explaining what this is in quantum terms. But you can still speak of individual photons as having a certain phase, such that whether it's gone horizontally or whether it's gone vertically, it's got this particular one thing. Both of the copies share this one thing. Or the better way of saying it, of constructing this explanation, is, as Chiara has said there, the property being in that particular superposition of paths. Okay, so it's in a superposition of paths. There could be many different ways and many different kinds of superpositions of paths you could have. If you change the energy of the photon, you'd have a different superposition of paths. If you change the thickness of the crystal, a different superposition of paths. But because you have a particular energy and a particular thickness of a crystal, amongst other things, the distance between, for example, the mirrors and the crystals would also affect this superposition of paths, as far as I'm aware. One thing that's different, and I keep coming back to this, is that the apparatus is physical. So the crystal is physical, and bouncing off the front surface is not symmetrical with passing through the crystal. Although you end up 50-50 in terms of the proportion of instances of the photon either going vertically or horizontally, the ones that end up going horizontally have passed through that crystal, and that has changed something about the photon. Call it the phase if you like. Whereas that kind of process has not happened with the one that bounces off and goes vertically. These two situations are not symmetrical, and therefore that comes to bear on what happens to the two instances when they recombine at the second crystal, causing them to always go off in that horizontal direction. And the reason for this is that on recombination at the second crystal, the interference could be constructive, could be destructive. There's different kinds of interference, and it happens to be the case that the interference is such that these two instances recombine such that the whole thing goes horizontally again. But the point here is, if you're interested in the physical properties of what's going on here, the actual physics of what's occurring, passing through and reflection, refraction and reflection if you like, are not perfectly the same kind of thing. And that's why it's not completely randomized. They're not the same kind of groups of photons. Whatever the case, it has this perfectly definite property. Let's keep reading. Chiara writes, that is why we see a definite outcome after the second crystal. A crystal creates a definite path superposition, then another crystal and a subsequent measurement of where the photon is constitute, jointly, a measurement of which superposition the photon is in. The outcome at the end is definite because after the first crystal, the photon is in a definite path superposition, but it does not have a definite path. Okay, pausing there, my reflection again. So once you've passed through that first crystal, you have a definite path superposition, but not a definite path. Not a definite path because it's 50-50. It's half of the instances are going vertically and half of the instances are being transmitted horizontally. So not a definite path, but a definite path superposition. For more on this, by the way, even more than what I've said, David Wallace himself, the emergent multiverse guy, actually has a lecture online about the Mark Zender interferometer from the multiverse perspective. And so there is yet more information from this way of looking at things out there on the internet. It's hard to find, but it is out there. Okay, so Chiara goes on to write, quote, "So there are two properties of the photon that play a role in the experiment with beam splitters. The property which path, call that P, and the property which path superposition, call that PS. Counterfactuals come in at this important point to explain the relation between these two properties in the case of quantum systems, such as the photon. If it is possible to predict the value of P, horizontal or vertical, with certainty, it is impossible to predict which path superposition the photon is in, and vice versa. When the photon is predictably travelling along a definite path and P is sharp, in the sense that the photon has a definite value of its position, the other property, PS, is not sharp. A measurement of PS yields an unpredictable outcome. But when the photon has gone through the crystal once, the outcome of a path measurement becomes unpredictable. Its position P is not sharp anymore, whereas the other property, PS, has become sharp. The outcome of its measurement is predictable. This relation between the two properties, P and PS, is based on counterfactuals, and, as I shall now illustrate, is at the heart of the notorious Bohr complementarity displayed by quantum systems. The fact that different properties of quantum systems, such as energy and position, or P and PS, cannot be simultaneously measured to arbitrarily high accuracy. Pausing there, my quick reflection. This is one of the most challenging parts of quantum theory, where there are many challenging things to accept. And some people just balk at it and just say it violates common sense, so they refuse to believe it. So let me try again. I think this is something I've explained a few times. It's tricky. You simply have to give up certain assumptions. Like, for example, we know that a car going down the street can, in a common sense way, be said to have a velocity. It's travelling at 60 kilometres per hour. And it also has a position. It is directly outside of the post office. So we can say these two things without contradiction, without violating our common sense notions, without seemingly violating any law of physics. The problem is we are violating a law of physics if we're going to take things really, really seriously. Newtonian physics, the way in which I just described things, or even Galileo's physics, allows us to say that the car has got this particular velocity, 60 kilometres per hour, and this particular position. And we are just so very used to speaking in that way that we think, how could it possibly be otherwise? But in quantum physics, it can be otherwise. Not only can it be otherwise, it simply is otherwise. The observables, the things like the velocity, the things like the position of the car, cannot be known with arbitrarily high accuracy simultaneously. We can't both know exactly what the position is and exactly what the velocity is. Now, it's unproblematic for a car because the car is so big. But when we get down to individual particles, it becomes significant. The effect is significant, measurable, noticeable, important. So we simply cannot say of something like an electron, it is precisely there and travelling at this particular speed. Now, there are many ways of getting to this truth. One is due to the fact that, well, if you were to try and find out what the position of an electron is at any particular point, think about what finding out really means. What finding out means is observing. What observing means is a physical process. You've got to interact with that electron. Now, you have to interact with the car when you look at it. But looking at a car means shining a light on it, seeing where it is, and the light doesn't affect the car. But in the case of the electron, if you want to know where that electron is, you're going to fire a photon at it. The photon is going to collide with that electron, so you know where it is. And that is going to affect the electron. And that photon can only give you so much information once that collision between the photon and the electron has happened, among other things. This is just the way the universe happens to be. So you simply have to just get over the sense that you can know these things simultaneously. You can't, and that's that. That's the way in which we understand the observations that we're making. The way in which we understand these strange quantum effects is precisely by speaking in this way. We cannot understand these. We cannot have perfect precision simultaneously of these two things. So you have to give up on this simultaneously knowing these two things at the same time. The rest of quantum physics only makes sense if you do give that up. But if you refuse to give them up, well, you're kind of in the position of rejecting that the explanation of the apparent motion of the sun across the sky is in fact not the motion of the sun across the sky at all, but rather the rotation of the Earth. Okay, the Earth revolving is the actual motion that's going on, causing the appearance of the sun to move across the sky. So making the mental shift to a rotating Earth, a revolving Earth, to a situation where quantum physics says of systems, they do not have a speed and a position. They have both, and they're intimately related. They are tied together. That's what we're talking about. That's the kind of shift in your mind you need to make. And this is all related to the fact that in quantum theory, remember, an object, let's be simple and just call it a particle. Well, a particle is actually a kind of complex thing. Although it's fundamental, that's one way of talking about it, it's not the case that it's just one single photon, as we've said before. And so when this thing we call a photon, which is not one single thing, encounters something like a crystal, as Chiara's explained, it ends up being in this superposition of states. The superposition it is in could be one of any number of possible superpositions. It depends upon the physical properties of the crystal, as we've said. But this idea of this single photon, it's deep, and you can just keep exploring it. And indeed, someone asked me recently about, well, do particles really exist? After all, isn't quantum field theory deeper? And in that theory, the field is the most fundamental thing, not the particles. And well, my response to that is, particles still exist. It's just that we can understand them through these fields. We can always get a better, deeper understanding of what these things are. It's not like the Greeks came up with what atoms are, these indivisible things, and then once they had decided what the theory of atoms were, we could never have a deeper understanding. Well, it turns out we still have atoms, it's just that we understand them more deeply. We know that they have nuclei and electrons, and those nuclei contain particles of neutrons and protons, and indeed those protons and neutrons contain particles within them as well. And so atoms become this rich area of delving ever deeper into our understanding of what this thing, an atom, is. The same is true of particles. We can call them vibrations of the quantum field. That's fine. We can call them an ensemble of fungible instances. Okay, these are all different ways of coming at the same idea. Our best understanding of what these particles are at the moment, these entities that exist within quantum theory are at the moment. And so because we get to these ever deeper understandings, our intuitions, not surprisingly, get pushed around. Let's go back to the book. Chiara writes, what does all this tell us of the information theoretic properties of the photon? The counterfactual property I've just uncovered provides the key to answering this question. In Chapter 3, copyability emerged as one of the characteristics of information media. Now you are about to discover that the copying task is much more ubiquitous than it may seem at first. It does not pertain to the world of computers and digital machines only. The task of copying and that of measuring anything physical are fundamentally the same. An apparatus that measures a given property is a system that, when given in input, some system, provides in output the value of the relevant property of the system as it really is. A kitchen scale is a familiar example of a measuring apparatus that measures the mass of things. When given some amount of flour, for instance, it gives an indication of the mass of the flour. If it is a perfect scale, when given an input of 1 kilogram of flour, it should give as a reading exactly 1 kilogram on its display. When provided, say, 10 kilograms of flour, it should read 10 kilograms exactly, and so on. The transformation that the scale realizes has precisely the same form as a copy operation because it copies the value of the mass given in input into the display of the scale. You have just encountered a new important fact, a fundamental link between different counterfactuals. Things that can be copied can also be measured, and vice versa. Another example of a measuring apparatus is the measurer of the photon position. It is a device that when given in input a photon travelling on the vertical or horizontal path, as in our earlier example, can display a message saying, respectively, photon on the vertical path or photon on the horizontal path. Once more, this apparatus copies the value of the path, horizontal or vertical, from the photon onto its display. Okay, so pausing there, just my reflection on this, very brief reflection. I find that a really cool result. This idea that copyability and measurability are the same thing, they're the same property. And Chiara says that properties that can be copied, she's going to call observables. Now I'm going to skip a significant part of the book here, and she talks about how, well, in the example, the P and the SP are not simultaneously copyable. And the reason is because you can't measure them both simultaneously. Well, you cannot measure them both to arbitrarily high precision simultaneously. And I'm going to pick it up where she writes. Here is an important and fascinating conclusion. Quantum systems have at least two observables, such as P and SP, which are not copyable jointly, or not measurable jointly, to the same arbitrarily high accuracy. It is a counterfactual property to do with what is impossible to perform on quantum systems. It also constitutes the crucial difference between the classical unpredictability of a coin toss and the quantum unpredictability arising with quantum superpositions, as for the photon path. Is that all there is to quantum systems and their counterfactual properties? No, there's more. You need another counterfactual property to capture quantum information media, this time about possibility. You need reversibility. Reversibility in physics usually refers to the possibility of reversing a transformation. A transformation is physically reversible if, whenever there is a way to perform it, performing it in the reverse direction is also possible. When you cross a bridge from one side to the other, you're performing a reversible transformation. Flipping a bit from 0 to 1 is also reversible. But cooking an egg is not a reversible transformation, nor is splatting the egg on the floor. A photon, when it behaves in a quantum way, must have the counterfactual property that all transformations allowed on it can be reversed. So if you apply, for example, the crystal on the photon, you should be able to use the crystal in reverse. So here is the main conclusion of this discussion. A quantum information medium is a system with the following counterfactual properties. Number 1. It has at least two information variables, such as P and PS, that are impossible to copy simultaneously to arbitrarily high accuracy, non-copyability of information variables. 2. It must be possible to reverse all the transformations involving these variables, reversibility. The smallest unit of quantum information is a quantum bit, a qubit. Photons, electrons, and other elementary particles can all be used as qubits. The reason why perfect qubits are hard to come by in everyday life, and the universal quantum computer is very hard to realize in practice, is that accurate reversibility is extremely difficult to achieve in practice, while at the same time preserving the other quantum properties of the physical object in question. Quantum theory says that it is possible, but it arises only under carefully controlled circumstances. Most photons around us, such as those emitted from the sunlight, do not undergo reversible transformations when left to naturally occurring conditions. Pausing there, my reflection. Yes, so this is the problem of decoherence. So we have the issue of trying to ensure that the quantum properties that are going to participate in a particular computation are going to be preserved over time without leaking into the environment, or rather without the environment leaking into our quantum computer and becoming entangled with our quantum computer. Now I'm skipping another substantial part of the chapter here, and I'm picking it up where Chiara is about to talk about entanglement and its relevance here. And she writes, quote, "Entanglement is one of the most exotic and powerful and misunderstood properties of quantum systems. When its properties were fully discovered, it soon became clear that it would revolutionize the way we understand composite quantum systems, that is to say, systems made of two or more subparts. The concept was already known to the pioneers of quantum theory. Schrödinger is usually credited with introducing the idea, but the full potential of entanglement-based ideas was unleashed in the early days of quantum computing, when that was first considered as a resource for quantum computation. The physicist Vlatko Vedrel, who in the 1990s pioneered our most subtle measures of entanglement, often jokes about the explosive development of the field, remarking that he managed to get an academic job simply by working on the foundations of this elusive and fascinating quantum phenomenon. Those were times when working on fundamental and adventurous topics was still encouraged in academia. In the current academic monoculture, pursuing transformative and risky projects is sadly becoming harder and harder." Pause there, my reflection. Yes, this is a modern yet perennial problem now in physics in particular, but science more broadly, that people become career scientists. What's wrong with having a career in science? Absolutely nothing, except that in the industry that is science today, at a university, for example, or at a research institute, what you are rewarded for is doing research, publishing stuff. If you need to demonstrate that you are a competent scientist according to your boss, then what you might want to do is to publish regularly. And if you're not publishing regularly, then your boss might start asking questions. The management, the administrators, what are you doing with all that time you have? Why are we giving you this money? You're not giving us any regular output. We need papers to be published in journals that say the name of the university that you're associated with. That's us. We need to be promoted out there so that students will sign up to our university courses. Sounds already cynical, but it's kind of the issue. And so what happens in that kind of culture is you have people working on small things, incremental things. They don't take a risk to really challenge the foundations, let's say, of physics and to make huge breakthroughs, because that takes a lot of time. You've really got to sit down for ages and ages and ages, and you can't waste your time publishing on small incremental things if you're aiming at the big discoveries. But how many universities are going to employ someone like that? How many research institutes are going to find interest in supporting someone like that? What they're interested in is public outreach, a way of demonstrating that, look, our university, our physics department gets published more often in more journals than anyone else. Look at how good our research department is. That's the metric. This is the problem with having such metrics, ways of determining who's a good researcher and who's not a good researcher. How else are you going to objectively, in scare quotes, assess one physicist, for example, against another physicist? If not, how often they're publishing. So this is why Chiara says, working on adventurous topics, topics which might very well fail. They're risky, and because they're risky, they might fail. But if they succeed, there's a huge upside. But universities may not want to take risks. Industry may not want to take risks. And this can kind of put a dampener on risk-taking and therefore progress. That takes us far afield from the chapter. That's just a little hobby horse of mine. Let's go back to the book. Chiara writes, quote, "Entanglement arises when you have two or more quantum entities interacting. For example, two photons or an electron and a photon. The essential feature of entangled quantum systems is that the information one can gain by jointly observing the systems is more than the information obtained by observing each system separately. This phenomenon is rather counterintuitive and removed from everyday experience." Pausing there, just my reflection. I would encourage you to, of course, refer to the book, and Chiara will go through an example to try and help you understand what entanglement is. And the way I like to think about entanglement myself is that you have something kind of fundamental like a particle, but if it's entangled with something else, then the two particles together are acting as a single system. You can't think of them separately anymore. They're not separate entities. They are a single system of particles, and the overall, the whole is greater than the sum of the parts, as we like to say, and entanglement is a form of that. And as Chiara goes on to say later, for example, with qubits, if qubits are entangled, quote, "It is possible to extract information globally, acting on both qubits, but impossible to do locally, acting on each qubit separately. This fascinating fact is not just curious, it is actually practically useful. For instance, if you wish to hide information in the two qubits, like in a safe, it is the base for entanglement-based quantum cryptography, where entanglement is used in order to transmit information securely by exploiting the fact that by looking only at the two qubits individually, it is not possible to guess the joint state of the two qubits." Pausing there. Entanglement is often used to try and, again, mystify quantum theory in all sorts of unfortunate ways. People will say things like it violates the speed of light restriction from relativity. This is not true. This is what Einstein was referring to with spooky action at a distance. The fact is, in order to entangle particles, that has to be done locally, And the measurement of particles has to also be done locally. And so then if you end up comparing one particle to another that are separated by a huge distance, and if you think the information is traveling from one particle to another faster than the speed of light, the only way you can try and establish that this is going on is to bring the two particles close enough together to compare them again. And that always happens locally as well. David Deutsch has written papers on this, that all of quantum physics is local. In other words, when we say local, does not violate special relativity. It doesn't violate relativity, the prohibition on exceeding the speed of light. Okay, that doesn't happen. There's no transmission of information faster than the speed of light. Entanglement doesn't show that. Bell's inequality doesn't show that. None of these purported ways of trying to get around the speed of light using quantum mechanical experiments show that at all. It's all local. Okay, so I'm skipping some more and I'll pick it up towards the end of the chapter where Chiara writes, quote, "With the physics of counterfactuals, features of quantum and classical information media can be expressed independently of the details of quantum theory or classical physics. The copyability of specific properties, the impossibility of copying others, and reversibility are general features about which we can talk without committing to quantum theory explicitly. They provide profound connections between intuitively very distant patches of the fabric of reality, such as photons, electron spins, neutrons, and other particles that would otherwise look very different, and yet they all have the same set of counterfactual properties. The power of the science of Kant is that it expresses the essence of quantum systems without ever committing to quantum theory's full machinery, made of specific laws of motion as a whole. This is important in view of the fact that, as I mentioned, quantum theory soon may be superseded by a better theory. My bet is that even if quantum theory eventually gets wiped away, the counterfactual information theoretic structure we have explored in this chapter will remain, because it has deeper foundations than quantum theory itself. These are the features that will survive the next revolution in physics. At a glance, all around you, things appear superficially very diverse, but when looking for long enough, and with the right spirit of scientific discovery, while also asking good questions and trying to play around with some bits here and there, sometimes we find a shiny, far-reaching connection between things that seem diverse and unrelated, and this connection is based on a unifying explanation of the distant phenomena in question. For example, physics tells us that a specific relation exists between mass and energy, between the finiteness of the speed of light and the structure of space-time, and, as you have learnt, between measurers and copiers. We have achieved yet another unification with the science of Kant. Quantum and classical information turn out to be two aspects of the same set of information theoretic properties. Quantum information media are a special case of classical information media with two additional properties, reversibility and the non-copyability of certain sets of states. Quantum and classical media are different, but perfectly compatible with each other. The fracture between the quantum and the classical world, the former supposedly aloof and incomprehensible, the latter more friendly and intuitive, has been healed. Realizing a unification of this kind goes together with abstracting away irrelevant details, making our understanding more general and robust than it was previously. These are promising features for a deeper understanding of nature, of which you and I are exploring the most basic building blocks. Once the edifice is built, it will be beautiful in its elegance and simplicity, and counterfactuals will be the robust elements of its foundation." End quote. That's the end of the chapter. So that's where I'll end the reading today, and I hope you agree with what I said at the beginning there, that this chapter really was able to do what I thought was such a difficult task, engaging the reader about quantum information theory, a highly esoteric part of the sciences. And if you've managed to understand this, pat yourself on the back, because even if you understood a small amount of this chapter, you'll be in a rarefied class of people who does understand this because of the way that it's presented here. I think anyone can understand this stuff, but they need to get a hold of the book. Good gift for someone actually who's showing an interest in science and physics and wants a new way of looking at the world and to have their intuitions challenged about some otherwise dry subjects, especially this particular one. Until next time, bye-bye.